Yeah, thank you. I will try my best to keep you awake after lunch. I would like to talk about wear detection on elevators. I presented, the first slide you will see, I presented 2011 here in Northampton. And at this time I presented a concept how to detect wear on elevators. It was based on a pilot project we did in the year 2003. And in the meantime, if you look into the elevator industry, and not just the elevator industry, there are a lot of systems coming up providing or promising predictive maintenance. And because this is such a hype, I want to show some things about the algorithms behind and also the technology behind. The first slide, as I said, I presented it already in 2011, is just to clarify what are the different maintenance ideas. So if you look to a graph where the wear reserve is presented over time, the so-called reactive maintenance, you install a component or a complete lift and you run it that long that you go under the damage limit and someone has to come fix a problem, and then in the ideal world you have again the reference condition and the same cycle starts again. This preventive maintenance, which is in 99% of all cases used for elevators, you do your maintenance in periods driven by time or driven by number of cycles, number of door movements or whatever. So in the end, you come very often, you are far away from the damage limit to get no breakdown, and you fix or prevent problems before they exist. The predictive maintenance, the idea is you go very close to the damage limit. That close that the lift is still running, but not failing. And proactive maintenance means you do things to increase your wear reserve. That's possible for lifts too. A good example are ropes. You are able to do proactive maintenance there to increase your rope lifetime. But it's really rare. But for both the predictive and the proactive maintenance, you need condition monitoring in a way that you are able to predict when the lift will fail. For sure, there are a lot of advantages. You minimize your downtimes, you maximize your lifetime of the components, you save costs, you can do the time schedule very well on airports, you do it in the night, whatever happens. But predictive maintenance, it's hard to achieve. So I'm not sure if the same term is used here, but if you look to the exhibition in Hanover, the Industrial Fair in Hanover, which is, I think, the biggest for all industries, there's a slogan called Industry 4.0. And if you look behind this slogan, there's not that much like the people are promising. So sometimes it looks a little bit like a conjurer. So predictive maintenance, if you look around, monitoring of wear and tear, efficient use of resources and so on, in the end, if you look a little bit deeper into the system, it is just related to time and cycles again. So it's preventive maintenance. For sure, it is very convenient to transport your controller data from the elevator, for example, into a cloud, but it is still preventive. You are still based on cycles. It is not predictive. It's a good way to do so. I completely agree, but it is not predictive maintenance. And then there's another part where big companies try to make us believers in clouds. That's a fantastic thing. So clouds are magic. I put tons of data into cloud, gigabytes per month or terabytes, whatever, putting tons of sensors to the elevators put them all to the cloud, and then I'm waiting for the magic thing in the cloud, and the cloud will say, good, bad, do that, do that. It will not happen. The idea for some clouds, so one model to rule them all, is not working. It's not working for complex machines like lifts are or escalators are. That is working for Amazon clouds. If someone buys a golf club, for sure he will need some golf balls or things like that. So it is working if you get a response. The cloud or the machine, the AI can learn if it gets a feedback. Then it is possible to learn. But with elevators, if you don't have the feedback, when did a component fail and so on, it is very, very hard to use machine learning. And especially for complex machines where it is significant where the lift is installed. So think about one lift model which is installed by 2 different installation teams. You will get different data from it, even if it is the same model. It is related to temperature, to the shaft. Is it from concrete? Is it from stone? How were the rails installed? And so on, and so on, and so on. It's very, very complex. Artificial intelligence does all the work. Nice idea. Imagine an artificial intelligence which is able to remove the signal noise, to find data outliers, things like that. That's impossible. It's not working. We tried ourselves with some clouds like the Azure cloud. There are some magic algorithms in it, and they are working great for humidity and temperature. Really good. You put both in, you give this temperature, and you know what will be the humidity. And it's working. But it's not working for complex machines, for a lot of sensors. It can work as soon as you put the domain knowledge into it. So if you use techniques like the digital twin, where you put physics into the cloud as well. So easy example, like you put the diameter of the rollers into it, and then you know which frequency will be related to the rollers, and then it might work. There are a lot of proof of concepts out there, and with really good results. But don't forget, if it works for one lift, it will not necessarily work for the next one, and it doesn't. So you need more general models. And also neural networks, we are using them too. They are good, but the effort to establish them for a big amount of lifts is not that easy. And it will for sure not work by putting tons of data into a cloud and waiting for a result. You need this domain knowledge. You need the ideas from engineers. And a very good example is this one. You will find it at Wikipedia. In the Second World War, the British, actually, they did an evaluation. They wanted to decrease the rate of planes which never came back. So they made this map by evaluating all planes coming back to the airports, looking where are the shot-ins, and to make the next planes more protected, to put armor on it. And they did. They sent the new planes, but the rate of planes never came back was the same. Nothing changed, because they didn't think about what they are doing. They made a map from all the shot-ins, But these are the shot-ins when the planes are coming back. So the cockpit, the engines, these are the important parts. So think about what you are doing. A better example where machine learning is working very well is this one. So this is the lifetime of an engine. We have the temperature in red, and we have the rotations in blue. And this area here is the temperature area in which the engine is allowed to work. At this point, the engine almost died. So it's really a defect in the engine. Looking to this graph, you could say, okay, at this point, I recognize that this will happen, the defect. Because here was a big peak above the temperature range, and then it is increasing, so it might happen there. A computer would detect it here, just by finding correlations. So because if you change your mind, not presenting the data over lifetime, if you present the data in this way, temperature above rotations, you clearly see a different view. So this dark blue points, this is the standard or the normal use of the engine. And as soon as you get points here in, you know I'm reaching the end of the lifetime. So the couple of temperature to rotation, that's important to look for. And this is something a cloud might learn. So from the basic idea we had in the year 2011, from the data from the pilot project in 2003, we designed such a module where we put a 3D acceleration sensor on top of the car. There is an option for load sensors as well. The thing is not connected to the controller, so we get no information from the controller. It is just powered. And it does the analysis on site. And it monitors all major elevator components. So something like that is able to monitor the gear, the engine, traction shift, the rollers, the guide shoes, if you are using them, the doors, very important. In the inner, there's a very strong computer in it. It's a bigger one. You can compare it to your office PC, which is doing all the calculations. It is related to an acceleration analysis in the end. So this computer is in real time detecting what is the elevator doing. Detecting the door zone, the acceleration phase, the constant ride, braking, leveling, if there is a leveling, and for sure door opening. And in all these different sections, we are calculating roughly 200 parameters per elevator ride. And we do that for every travel, really for every travel. And these different parameters are related to special components. For example, during the constant ride, with frequency analysis, you learn a lot about the engine, the gearbox, the traction shift, and also the rollers. And things like this are used to find problems. What's happening in the inside, from a software part of view, there's an acquisition thread which is sampling all the data all the time. It is written into a ring buffer. Then there's an indexer thread. It is roughly delayed 1 microsecond to real time, which is doing the separation into different travel sections. After this has happened, it is written into a database, and as soon as the computer has time again, it is reading that out from the database, doing the evaluations of these parameters, interpreting the results, and sending alarms, if there are alarms, into a cloud. The basic idea behind this, we are collecting 200 parameters. They are related to the current load in the car, and they are related to the current floor where the car is traveling. So it is 3-dimensional. In the end, for an installation with 10 stories, we create roughly 12,000 curves over time. No human can evaluate them. So that's done by the computer itself. And we are using, in principle, this one for the different components. If you put a new component into service, you usually have a fast decrease of the wear reserve and then a more or less stable zone. This is really the zone you are using. And close before it comes to a breakdown or you're reaching the damage limit, the curve shows significant changes. And we are looking for such significant changes. Not for sporadic ones. So by doing statistics, we are eliminating sporadic events. And looking for these 12 or 13,000 curves in this way to find significant changes, we produce alerts like this. So that's a real example done in Singapore, where we have some pilots running. This elevator is giving some alerts for the driving unit, so for the whole component group. And it faced during the constant ride some anomalies, yeah, something like that. If you look deeper into the data, so you are able to get the raw data from the system. These are the accelerations. So the blue one is the acceleration in Z, the vertical acceleration. Car stands still, accelerate in down direction, constant travel, decelerate, stand still again. And these both are the horizontal vibrations in both directions, and this is the speed. So before these alerts came up, a curve looked like that. Not good, so it's not a smooth elevator, but okay. During the alerting, the curves looked like that, so really different. So the computer found, not by comparing two curves, by looking to all travels for all days, for some days, found significant changes. Someone entered the elevator and looked for, and found that the controller card of the frequency inverter wasn't working anymore, not really well. And so they replaced the controller card and got this results later on. Again, not good, but this, in this curves, it was shown that the controller started to get problems, which in the end would result in a fail. I'm almost done. Shaft efficiency, that's another thing you can monitor with this system. So how much energy you are wasting just for friction. This is our play elevator in Braunschweig, Germany, where we can do almost what we want. It is a 13-story building, residential, with guiding shoes. So what we did, we dried the rails. So we had a really, really bad efficiency. And then we oiled them again, and the efficiency increased. Another example, I make it short. A group of elevators, A and B. These are the curves from B. These are the curves from A. You see, especially A looks bad, especially in the Z direction compared to B, which is on top. The ride quality is really poor by the lower one, better by the upper one. And again, without connection to the controller, this is why it happened. This one just makes almost a quarter of all trips. So the group controller is not working very well. Okay, I'm done. It is a short time to present it in 15 minutes, so I cannot show really everything. But I'm pretty sure predictive maintenance will come, and there are a lot of advertisements for predictive maintenance, also for lifts and escalators and the other industries. Right now, there are not many systems really working predictive. I'm pretty sure there will be a lot of new challenges, especially for the mid-sized and small companies. The big ones are prepared. to change their service model, or they're just changing their service model. But the mid-sized companies, they will face big troubles, I guess. And what concerns me a little bit, there are now companies coming into the elevator and escalator market which are not located originally in this market, which are also not connected to one of the players in the market, which are just wanted to get our best business, which is a service, where we all are related to. And these companies try to bring models into the market which make it feasible to, I'm not sure you know this My Hammer website in the internet. Perhaps there's a different name here in UK or in US, where you just send out an order like, I need someone who replace a traction sheath or who replace some rollers, driven by predictive maintenance to bring other companies into the business. Okay, so I'm almost done. Thank you very much for your attention, especially all the native speakers. Thank you for your patience with my English.